The universe, vast, mysterious, and almost incomprehensible, stretching billions of light-years, it holds secrets that have puzzled humanity for centuries. Today, we dive deeper into some of the most fascinating facts about space, exploring the wonders of stars, galaxies, and the instruments that help us uncover these cosmic mysteries. One of the greatest challenges in understanding the universe lies not in looking, but in communicating. When it comes to interstellar distances, information does not travel instantly. A message sent from one star to another might take years, decades, or even centuries to arrive. Imagine trying to have a conversation with a star system hundreds of light-years away. By the time you receive a response, generations may have passed on Earth. Scientists working on interstellar communication must account for these extreme distances. Signals weaken, time becomes a barrier, and even with the fastest technology, sending information across the cosmos requires patience and precision, unlike anything experienced on Earth. Within our galaxy, there are regions where stars are not isolated but packed densely together. These regions are called globular clusters. A single globular cluster can contain hundreds of thousands of stars, all gravitationally bound and orbiting a common center. To put this into perspective, while the average distance between stars in the Milky Way can be several light-years, stars near the core of a globular cluster can be separated by just a few astronomical units, sometimes close enough that neighboring stars might interact in dramatic ways. Globular clusters are more than just stellar communities, they are also time machines. Since they formed early in the universe's history, their stars are ancient. By studying these stars, astronomers gain insights into the conditions and processes that shaped the Milky Way and other galaxies in the early stages of their existence. Additionally, globular clusters play a significant role in our understanding of black hole formation and the dynamics of extreme gravity. Some of these clusters have supermassive black holes at their centers, making them ideal laboratories for studying the behavior of matter under intense gravitational forces. Understanding these processes not only deepens our knowledge of astrophysics, but also helps us comprehend the fundamental laws that govern the universe. Moreover, globular clusters are surprisingly diverse. While some are relatively peaceful, others have undergone dramatic events that have disrupted their structure and thrown stars into unusual orbits. Astronomers believe that interactions with other galaxies, the passage of giant gas clouds, or even the formation of second black holes within a cluster can cause these violent events. As we continue to observe and analyze these stellar communities, they promise to reveal even more secrets of our cosmic origins and evolution. Our galaxy, the Milky Way, is not just a simple spiral of stars. It is home to over 100 globular clusters, each containing hundreds of thousands of stars. These clusters, densely packed with ancient stars, orbit around the galaxy, providing a glimpse into the Milky Way's past. The sheer number of stars in these clusters poses logistical and computational challenges for astronomers. Each cluster contains hundreds of thousands, if not millions of stars, all of which are in constant motion. Tracking and analyzing the positions and velocities of these stars requires sophisticated algorithms and high-performance computing. The complexity increases when studying multiple clusters simultaneously, as the interactions between the stars in different clusters must also be considered. Furthermore, the age of the stars in these clusters presents its own set of challenges. Since they formed early in the universe's history, billions of years ago, studying them helps us understand galactic evolution. However, analyzing the properties and behaviors of stars that are billions of years old requires specialized techniques and equipment. Despite these challenges, advancements in observational technology and data analysis methods continue to provide valuable insights into the nature and evolution of globular clusters. By overcoming these hurdles, astronomers are uncovering the secrets of these stellar communities and gaining a deeper understanding of our place in the vast universe. Sometimes the best things in life come unexpectedly. That's certainly true for the two powerful optical telescopes that NASA received from the National Reconnaissance Office. These instruments, initially designed for Earth observation, turned out to be incredibly versatile and have been repurposed for astronomy. But getting these telescopes wasn't a straightforward process. It involved extensive modifications and investments to adapt them for space observation. The first step was to remove or deactivate the original sensors and instruments that were designed for Earth observation and replace them with new ones suitable for astronomical research. This included replacing cameras, removing protective coatings, and installing new instruments for detecting and analyzing faint cosmic signals. Next, the telescopes needed to be integrated into the Space Observatory platform, which involved mounting the instruments securely, integrating them with the spacecraft systems, and ensuring they could withstand the rigors of launch and operation in space. Once in space, the telescopes required precise alignment and calibration to function optimally. This involved adjusting the optical elements to focus light from distant objects onto the new instruments and calibrating the instruments to ensure accurate data collection and analysis. Overall, the repurposing of these telescopes for space observation has been a remarkable achievement in engineering and scientific collaboration. The successful integration of these instruments into space observatories has enabled groundbreaking astronomical discoveries that would not have been possible with conventional ground-based telescopes. The story of these telescopes highlights the ingenuity and adaptability of both the engineering and scientific communities in pushing the boundaries of space exploration and discovery. Owning advanced telescopes is just the beginning. Operating these instruments in space requires a host of additional electronics, sensors, and instruments. Despite receiving the telescopes for free, NASA still invests heavily in these technologies. Take, for example, the James Webb Space Telescope. It is equipped with 4 main instruments: a near-infrared camera, a near-infrared spectrometer, a mid-infrared instrument, and a fine guidance sensor. These instruments were not only expensive to develop and build, but also require a significant amount of power to operate. According to NASA, the total power consumption of the James Webb Space Telescope is approximately 225 watts. This power is supplied by solar panels that convert sunlight into electricity. Additionally, the telescope requires a large and complex data handling system to process the huge amount of data generated by the instruments. This includes computers, storage systems, and communication systems to transmit the data back to Earth. The complexity of these systems highlights the immense amount of work that goes into operating a space telescope. For instance, the James Webb Space Telescope had to undergo rigorous testing to ensure that all of the components could work together as intended. This included testing the telescope's ability to maintain its shape and focus in space, as well as testing the performance of the instruments under various conditions. Furthermore, operating a space telescope requires a dedicated team of engineers and scientists to monitor the instrument, maintain it, and analyze the data. These individuals work around the clock to ensure that the telescope is functioning properly and to make the most of the limited observation time. The cost of operating a space telescope can vary depending on the specific instrument and mission, but it is safe to say that it runs into millions of dollars per year. Despite the cost, the scientific community recognizes the importance of investing in these instruments as they provide a unique and powerful way to explore the universe. The James Webb Space Telescope, for example, is already making groundbreaking discoveries in astronomy. Its advanced instruments and capabilities are allowing scientists to see things that have never been seen before, such as the first galaxies that formed after the Big Bang. In conclusion, while operating a space telescope is expensive, it is a worthwhile investment that is expanding our understanding of the universe and pushing the boundaries of human knowledge. In our quest to unravel the mysteries of the cosmos, we often rely on advanced tools to peer into the depths of space. Among these instruments, X-ray telescopes hold a special place in helping us probe the most extreme environments in the universe. X-ray telescopes enable us to observe phenomena that are invisible to the naked eye or traditional optical telescopes. They allow us to see supermassive black holes, study the hot gas in galaxy clusters, and analyze the remnants of exploded stars. However, these telescopes present unique challenges due to the nature of X-rays. They require specialized mirrors and detectors that can withstand the intense radiation and focus the X-rays onto detectors without being damaged. This is achieved by using materials with high atomic numbers such as gold and platinum, which have the ability to reflect X-rays effectively. The use of these materials not only makes the telescopes incredibly complex, but also significantly increases their cost. Additionally, the mirrors and detectors must be kept at extremely low temperatures to prevent thermal noise from interfering with the observations. This requires sophisticated cooling systems that add to the overall complexity and expense of the telescopes. Despite these challenges, X-ray telescopes have revolutionized our understanding of the universe. They have enabled us to discover pulsars, study the evolution of galaxies, and explore the surfaces of distant planets. One of the most famous X-ray telescopes is the Chandra X-ray Observatory, launched by NASA in 1999. The observatory's high-resolution cameras have allowed scientists to capture stunning images of celestial objects and gain unprecedented insights into their properties. Another notable X-ray telescope is the European Space Agency's XMM Newton, which has been in operation since 1999. The telescope S3 X-ray telescopes provide an almost 360-degree field of view, enabling it to survey large areas of the sky for X-ray sources. These are just two examples of the incredible X-ray telescopes that have advanced our understanding of the cosmos. As technology continues to improve, we can expect even more powerful telescopes to be developed, allowing us to probe the universe in greater detail than ever before. These 5 facts only scratch the surface of what makes space so incredible. From densely packed stellar cities to the challenges of communicating across light years, the cosmos constantly reminds us of both our curiosity and our limitations. In our next segment, we will explore black holes, exoplanets, and the astonishing phenomena that make the universe truly awe-inspiring. The universe is vast, mysterious, and ever-expanding. With every telescope, every new mission, and every discovery, we inch closer to understanding the cosmos. And yet, there is always more to explore, more to question, more to marvel at. Stay tuned with Beyond the Theory as we continue our journey through the top facts about space, revealing the wonders of our universe one discovery at a time.